Well, good morning, everyone. This is Scott on our first day of distance lecture. So, we'll see how this goes. Bear with me. Today, we're going to talk about simulation first, and then get in a little bit into kind of what we're going to do for the exams moving forward. So, before we get into that, we did have some homework that was due today. Please email this to me, hopefully before you get to this lecture, but at the same time, it's okay if you do it afterwards. It's more just if you copy what I say, it's not really hoping you learn too much. So hopefully you got this done. The first question we have is how many elements will be compared to target? So target's the thing we're looking for an unsuccessful binary search in a vector of 1,000 items. Then we also need to consider what is the answer going to be for 2,000 items. Now, the thing that's important about this question is going to be the fact that we're looking for an unsuccessful binary search, right? If we were doing a successful binary search, we can't really tell how many elements we're going to compare because it's feasible that the very first element we check is the element we're looking for, right? That's absolutely best case scenario. We're looking for value 5, and value 5 is the first thing we check for. Now, that's unlikely, especially given that we have 1,000 items. So if we know nothing about the 1,000 items, right, finding a single element, we're looking for, 1 in 1,000 chances, or 1 in 1,001 if we're considering the case that it's not found at all. But the cool thing about binary search is that it turns out we can get there faster than just 1 in 1,000. We can do that much quicker. So let's do this first case where we're looking for 1,000 elements first. Now, the very first thing wrong way. The very first thing that's going to happen is going to be we check the very center or the pivot value of our array. So we're going to essentially be checking the value that's right in the center of our array. The way we're going to do this is take the size, divide it by 2, and then look at that value. Now, one of the elements of binary search is going to be that if it is less than that value, we don't need to check that value again. So I'm going to take n divided by 2 and then subtract 1 from that to get this 499, right? 1,000 divided by 2 gives me 500, but I'm never going to check that 500th element. I'm always going to check one less than it, right? Once I've determined it, I don't need to come back to it. So that's where I'm getting this 499 number from. So then I'm going to call a binary search function, if I'm doing this recursively, on this array that is 499 elements long. That one step is only one single comparison. So if we're keeping track, that's just 1 on our comparison count. So we're going to keep going through. We're going to go from 499 down to 248, from 248 down to 123, 123 down to 60, right? These aren't lining quite up because when we take a number like 499 and divide it by 2, we're getting some rounding issues, which in C++ we're doing integer math, so we're going to be rounding down, and then I'm still subtracting 1 from that. Now, it turns out that binary search doesn't really care about this rounding error. All it cares about is if it needs to be checking above or below its current value. Oh, that's fun. There's a smoke detector in my house going off. That'll be a good time for the rest of the lecture. All right, so it's going to get too small for me to handle. So at this point, I'm going to kind of expand 60 and then keep going. We go from 60 to 29 to 13 to 5. Then I'm going to do the same thing where I expand 5, and then 5 to 1. And then we have one last base case, which is essentially realizing that we are looking at an empty array. There's nothing left to check. We then can call or recursively collapse our stack back up, saying, hey, we looked through everything and we're done. Now, if we go through, every single one of these calls is going to be a single comparison, right? We're looking for the comparison operation. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. This last one isn't actually doing a comparison. It's just doing a comparison on the size. So I'm not going to count that. So that's where I'm getting to this 12 total checks, but we're making 13 function calls. I just want to make a slight distinction between those two things. Okay, that's pretty great, right? We are saying that for all cases, the maximum number of checks we will ever have to do for an array of 1,000 is going to be 12. That's nice, right? If we're doing a linear search, we're just starting at 0 and going up. That's going to be worst case, 1,000 total checks. So we already see a pretty big improvement just right there. Now, the cool thing is if we take this one step further and we ask, okay, what happens if we double the size of our vector? Now we're looking at a vector of 2,000 items. Linear search, this is going to be 2,000 possible comparisons, especially in the case where there is an unsuccessful search, right? We're looking at an array and we don't find the item. That guaranteed with a linear search is going to be 2,000 items. So we've essentially done a times 2 increase going from 1,000 to 2,000, right? No matter what linear search, it's going to be a times 2 multiplier. But for binary search, it turns out that it's a lot simpler than that. The very first step of our binary search is going to be going from an array that is 2,000 elements long down to an array that is 999 elements long. And now you might see the pattern that I'm going to show you. That's suspiciously similar in size to an array of 1,000. And we already determined that for an array of 1,000, we had to check 12 times and we had to make 13 function calls. So we can, without doing extra math, reasonably assume that for an array of 999, we're going to have 13 total checks and 14 function calls, right? We're just adding one extra function call for this 2,000 to 999, and then we're just going to take the totals for our 1,000 and go into our 2,000. And right, the reason I think this is an interesting question is that this is showing the power of binary search. If you're looking at an array of 10 elements, it's not that much different than doing a linear search. But imagine if you're doing, right, 500,000 elements, right? That's a pretty significant change in going from linear search up to binary search. Now, again, remember, binary search doesn't solve all of our problems. Binary search has to be on an array that is already sorted. We're going to come back to sorting algorithms in 2 or 3 weeks, so we'll talk more about why that's kind of an issue and why we need to deal with that. And it turns out there are ways that we can deal with it in pretty efficient ways. All right, cool. Next question we've got. We have this question of if there are multiple occurrences of the target item in a vector, what can you say about the subscript value that will be returned by linear search? Additionally, what is going to be the subscript value that is returned from binary search? Now, this is getting at the behavior of each of these searches, and the behaviors come into play on what the information that's being passed is. So in this first case, linear search, we're always going to be starting from either the front or the back of our array. So that means that when we are moving forward, our I value is going to be checking the first element and then moving forward and checking the second element, then going to the third element. We're going to be continually checking every one of these elements. So that means that if we are looking for a 4, right, we're looking for one of these 4s, the very first one we're going to check is going to be the first one. No matter what, always linear search is going to go 0, 1, 2, 3. We will always return back this 4. Now, I say last in here too, because you could do a linear search going from the back end. But then that means you're always going to check, not that one. You're always going to check that last 4, no matter what. Again, no matter, right, it doesn't matter what the 4s look like. It'll always check either the first or the last one. Now, that could be beneficial for us, right? There could be a reason we might want to know the first, because imagine these aren't numbers, but instead they're objects. And so, right, it's just an object that has a 4 as its key value, but it might have some internal information that's different. So that's a reasonable thing to care about. Now, on the binary search side, it turns out that there's no real guarantee of which element we're going to be accessing because we don't necessarily have a guarantee on the way the binary search is going to filter through our array. So in this case, if I'm looking for 4, the very first thing I check for is going to be half of the array, and then I'm going to round down, so I'm going to check that guy. So I'm checking this index, and that's a 4, so I return back. I don't have a guarantee of where this 4 exists in relation to the other 4s. It just happens to exist here. That's all I really care about. So the same is true if we look at something like 2, right? If we're filtering down our binary search, we're going to check this value. Then that means we're going to check the array that's just these 4 values. When we go to the midpoint or the pivot, we're going to check here. And hey, we found our 2. Now, again, I don't have a guarantee that this is the last 2. I can tell via pattern recognition that it is the last 2, but that's not necessarily a guarantee. So the whole point here being that binary search is just going to give you a subscript. It's not necessarily the first or the last or the middle even. It's just going to give you some subscript of that element. Cool. All right. If you've got questions on those, feel free to email me. Feel free to bring those up in the class chat later today. We can get deeper into that. All right. So for today, I want to go over kind of this idea of simulation and why data structures are important for solving problems. And really, simulation is a good motivator for how and why we need to care about these things. And then I want to get into kind of the path forward and how we're going to do exams and kind of get into exam 2. All right. So abstract data structures lean pretty heavily into how simulations work, right? We're going to use abstract data structures in all kinds of things, but in particular, they're helpful to think about in this form of simulations. And the idea here is that most simulations are going to be exposing some kind of real world analog to a data structure. The book uses an airplane simulation, and that's actually what I'm going to show you guys in a little bit. Right. So if we're doing this airplane simulation of getting into a queue and waiting, right, that's analogous to using a queue. It's the same name, right? The queue data structure is based off the idea of a queue. If you recall back to our example of the elevator in using a queue, right? It's the same thing. We can think of people waiting in line for something as a queue, but we can also think of things like, I don't know, if you're watching Netflix and you're watching a TV show, you're going to have a queue that's coming in from the Netflix servers that is the queue of the frames of the video you're going to be watching, right? The frame that comes in first needs to be in place before the frame that comes in second, right? So that's a queue. That's a functional data structure in terms of how that video is going to get pushed through. But if we think about other simulations, right, we can start to think about things like, well, we can start to simulate traffic, right? A road in just itself is pretty similar to a queue, assuming that you can't change lanes, right? A single lane road between intersections is just a queue. When we start thinking about network simulations, so the connections between different points, we're starting to get into if these are stacks or queues. I didn't want to change the slide from last time I gave this lecture, so I kept this in here. Epidemiology simulations, right? Getting into how viruses and diseases spread throughout a population. These are all going to be similar kind of problems that can be approached with a data structure, right? We can start to consider how things are going to move through because we can start to form relationships between different objects. Right. You already saw my elevator simulator, right? We can move forward from that. But the goal here is that we can start to think about problems in more complex ways, leveraging data structures to help us with that simulation. All right. So I actually want you to pause this video in a second. I want you to go watch this video by CGP Grey. He's a fantastic YouTuber and kind of a video essayist. He dives into a lot of interesting things that I think you will like. But this particular video is going over how we can board airplanes in a more efficient way. And he doesn't approach this from the standpoint of data structures, but it's still a thing that we can glean some information off of based on how the simulations could be run if we were to do it analytically, as opposed to kind of how he's doing it, which is both referencing other sources and animating it, right? And he kind of references the disjunct between animation and the actual simulation. So as you're watching the video, I want you to pay attention to and think about, if I were to solve this problem, if Scott were to give me an assignment that's like, hey, figure out what the best method is for loading a plane, right? Think about what data structures are you going to use to do that. So go ahead and pause this video. I'll be here. I'll wait. Go find this YouTube video. There's a link in the description of this video. Go watch that. Think about what data structures are being used, then come back. All right, cool. So hopefully you enjoy that. I like that video a lot. I've watched it all the time. It's good. It's also frustrating, but it's good. So, right, the data structures that are being used. Well, you probably saw a lot of queues, which are the specific lines that are used to get into the plane. And then also that aisle and the jetway, right? That's all one single queue that's getting into the plane. And then the seats themselves form stacks, right? There's that conversation around seat shuffling. That's just a stack. You have to pop people out of the stack to then push other people in and then re-push the other people, right? You're doing that shuffling back and forth between different stacks. Okay, So this leads us to this interesting question of, well, why do we want to simulate, right? Why would we spend this time talking about data structures and simulation? Well, this gets into the idea that we can do things in a virtual space and test the idea before we ever have to implement it. This is a huge benefit as we start scaling up problems. If I ask you, okay, how do we sort an array? Okay, you could come up with this idea of, well, we might be able to use a stack to do that. And that's fine because the problem is small enough and tractable enough for us to really understand the environment. But simulations allow us to get much bigger in terms of what we are doing and what we are testing. And so we can use simulations to do these tests in a way that is significantly cheaper, right? I have this example of think about implementing a space mission. This is actually some work that I do with Dr. Sankaran Kamesh. Over the summer, last summer and this summer, we're going to be working on this problem of trying to hit an asteroid with a spaceship. Now, if we were to do this physically, it would take millions of dollars to do, right? We have to make a rocket. We have to send this rocket out into space. The rocket may or may not hit its target. Now, what we can do is we can use simulations to calculate that, to simulate, to find the emergent behavior without any of the cost of the mission, right? The cost to us is the hardware to run it on, which we're using GPUs. And in the development time, which is no small task, right? We worked past the last summer where there was about 5 of us working on it. And this summer there's going to be close to the same number. So that's not free per se, but at the same time, it's way cheaper than a couple $1 million to launch a satellite, right? So the idea here is that we can simulate very wide-reaching and very impactful things in a what-if kind of scenario, right? We can optimize that design by performing the what-if analyses. Now, some of these, right, when I say cheaper, I don't just mean cost, monetary cheapness. I also mean time cheapness. If I'm sending a mission to hit an asteroid, that's going to take 2 years. Well, if I'm going to do this using an iterative design process, I want to, test something, tweak it, test something, tweak it, test something, tweak it. That's not going to work, right? That's going to take me way too many years. And our simulation that we're running for this NASA mission, we're running 300 simulations every generation. So we're doing a genetic algorithm. We run 300 simulations. We see which ones are working well. We then do another iteration where we run another 300 simulations. And we're able to do these simulations, right, in massively parallel, in massively time compressed ways, right? It takes us a couple hours to test hundreds of thousands of simulations, right? And I'm kind of beating this into the ground, but the whole point here is that we can simulate very interesting problems in a very inexpensive way, right? And this is getting towards the idea of emergent behavior. It turns out that the more complex something is, the more interactions there are, the more that the behaviors are hidden from our pattern recognition, the harder it is for us to predict or to engage with, to understand the space. And simulations can lead us towards deeper understanding based on the emergent behavior of the system. We can, we can put in rules in place for like an elevator simulator of, most people are going to leave their apartment building at sometime between 7 and 9 in the morning. They're going to come back between 3 and 5 in the evening, right? They're going to have a random distribution throughout the building. Well, once we understand that, we can start to develop a heuristic algorithm and an algorithm that looks towards solving the problem, understanding what those emergent behaviors are. And it turns out that you'll want to have your elevator somewhere in the middle of your building in the morning by default. And then in the evening, you're going to want it at the lobby, at the base floor on average, right? If nothing's happening, have it sit on the base floor. And that problem is not too complicated, but you can imagine that if we start introducing even slightly more complexities to that example, we're going to need simulations to help us to understand that. So I just want to plant this seed right at this point in the course, because as we move forward, what you guys will be doing for your final projects are going to be taking the things we've learned in the class and then implementing your own simulation to solve some real world problem, right? That's the direction we're going. And now that we kind of have a good understanding of what those data structures are, we can start to think forward to, well, how are we going to use those data structures to then solve real world problems, right? That's the direction we're going. All right, but before we can get there, we got to talk about kind of the path forward for the class, and then I'll also give you a kind of overview briefing on the exam. All right, so a couple questions that I've been getting a fair amount, so I just want to address them with the whole class. First question that I've been getting a lot is, will the projects be group projects, right? We have 3 projects left in the class. Initially, they were going to be group projects. And what I'm going to say for group projects is that if you would like to, you can do them as groups. We can use the live share option inside of Visual Studio Code to do pair programming remotely. That's fine. I'm not going to change necessarily the difficulty of the problems. They're going to stay similar. But at the same time, I'm going to let you opt into being in a group. If you'd like to be in a group, that's fine. Before we assign the project, I will ask everyone if they want to, right? I'll basically send an email saying, let me know if you want to do this as a group or if you want to do this individually. If you choose to opt into a group, I'm still going to make those assignments. What I want to avoid is people only, working with people they like or only working with specific other individuals. That leads to a lot of potential problems. So I'm going to make it that if you want to do a group, you can let me know, and then I'll put those people into a pool, and I will randomly match those people moving forward. We're going to have the same rules that you can't work with people that you've worked with in the past, right? We're going to keep all of those things in place. However, if you want to work on it solo, that's okay. You can. I get that coordinating is going to be a little challenging, kind of with the distance aspect. All right, so the next thing is going to be final projects. Yep, we're still going to have final projects. And again, I'll give you a heads up right now. They're going to be simulation-based. You're going to be simulating some kind of phenomena. The same thing here. I'm going to make the projects optional to be in groups. But the big difference here is that I will allow people to self-select into groups. If there's a person you want to work with and you work well with them, that's okay. You can work with them on the final project. Now, another question is around this idea of do you have to participate in our class? And I'm using quotes because, right, this is the content of the course. This lecture is the content. But then I'm still going to be having these Monday, Wednesday, Friday class sessions that'll be in Discord, and we can talk through problems and clarify questions, that kind of stuff. That's what I'm referring to as class, is the Discord sessions. No, you don't have to participate in that activity, right, in that conversation. The reason I really want to lean into this is because I know that there are some people that either, they don't have access to internet that's reliable, they don't have access to a computer at that time, they're in a different time zone, whatever the reason is. I want to make sure that you can engage with the material in whatever space and way works best for you. So no, you don't have to participate. I would highly suggest it. And if you can't participate in the time, I would highly suggest that you still listen to the streams. I'll be posting them to the Discord channel after they're done. I'll make sure that is all recorded so that if you didn't get the opportunity to participate, you can still access the conversation. If you know that you have some questions, but you're not going to be able to engage, you can send me an email ahead of time and just be like, hey, for class, could you talk about this thing? I'm still a little fuzzy about that. Could you walk through and talk through that thing? That's more than fine, right? You don't necessarily have to only consume what other people ask questions. You can ask questions ahead of time. But again, I would highly suggest it. If you see this as an excuse to then, not participate and kind of just watch the lectures as you will and do the projects on your own, you're going to miss some stuff. It's going to be pretty hard for you. So again, I would highly suggest participating with these class sessions. But at the same time, I'm not taking attendance. If you can't, that's fine. We can work around that. All right, so let's look at a modified schedule. Now, I know the text is kind of small here. I'm going to be posting this to Blackboard so you can have a hard copy of it. You don't have to search through a random YouTube video to find it. This is our condensed schedule. The only real thing I took out was we had a single lecture on advanced tree operations that I removed. The lecture itself is challenging. Like, the things that are going on in that lecture is already hard to begin with. And it's kind of a secondary benefit. We're still going to be spending 2 full days talking about trees and how they're implemented. But I took out the lecture on advanced trees just because it gets a little weird. Everything else, though, is the same. I shuffled everything down into this last week to do the final project work, and I removed the class selected lecture. If you guys want me to do that, I still can, but I'm not going to make a class around it. So the last couple of days of the class, I'm just going to make open for you to work on your final project. I'll be around if people have troubleshooting questions, stuff like that. But everything else in terms of content is still there. I then also shifted around some of the due dates to fit this new schedule. I will make a good effort to post with every project the due date with the project, so you don't have to refer to this. You can just see it in that project. The very first thing that's going to be due is going to be exam 2. We're going to assign it today. It'll be due on Thursday. This Friday, we're going to get into trees, so we'll start the project on trees. That will then be due basically in 2 weeks. You get 2 weeks to work on that, as well as working on heaps, which will be the same project. All right. I think that's going to be okay for the schedule. Again, if you have questions, let me know. And again, I will post this on Blackboard so you can see it in a little bit more straightforward fashion. All right, so the exam. The feedback that I got from you all was extremely polarizing. I don't think that's necessarily a problem, but I just want to make sure that you know that if I'm not going the way that you thought I was going to, it's because there's a lot of opinions and a lot of feelings. It turned out that there were equal number of people that picked getting rid of exams altogether, as there were people that selected that veto option to not get rid of exams, right? So again, I want to be very careful about how we change the course because we've already been doing the course. So I want to be careful about that. So I think what we're going to do in place is a good kind of happy medium between all of the 4 options there of doing exams regularly, doing the exams with open book, open internet, doing practical exams, doing no exams, right? We're going to kind of fit into all of those. So what we're going to do is that I will push out the exam on Wikit. It'll show up in your personal repository in our class. Each person is going to get that exam repository, and in that repository, there will be 2 things. One will be a markdown file that's going to be kind of long form questions that I want you to answer. This is going to be similar to like a conceptual portion of an exam, but it's going to be a little more open-ended in the sense that I want to hear your thoughts, your understanding on the questions. The other part is going to be some kind of practical portion in which you have to either implement something or you have to demonstrate something using code, right? So there's going to be a mix of the 2. My goal at the moment is to make the exams take about 3 to 4-ish hours, right? That's going to be, well, I should say it's going to take 2 to 3 hours. That's going to be my goal. So if you're, procrastinating and you're about to start working the exam right before it's due, you're going to need some time to work on them. They're going to be pretty challenging. So in terms of timing for this first one, I'm going to push it as soon as our class, quote unquote class time is done today. So that's going to be about 2:00 today. I will push out to everyone the first or the exam 2 into your Wikit folder. And then it's going to be due on Thursday, this coming Thursday. Now, I know a lot of you have a hard time when I say something like it's due Thursday. You'll ask me, well, what time Thursday? So I'm going to put a due date on it. If this helps you, great. If it doesn't help you, you can treat it as Thursday and just get it done by this time, right? So the due date's going to be 10 p.m. Pacific Standard Time. So I'm going to do everything in reference to myself. I know not all of you are are on the West Coast. That's fine. I'm just putting a flag in the sand, and you can treat it with what you want. All right. So a couple expectations I want to point out. The first is going to be that this is an open book and open internet exam. I don't expect you to not use those resources. You can use lecture slides. You can use any of these streams or videos or whatever you want. But, and this is huge, you have to cite your sources. If you use something that's not your brain, you have to cite it. And it has to be a full citation, not just, I looked online, right? It has to be the website, preferably like the exact page, preferably the exact paragraph you pulled it from. If it's from the book, give me a page number, right? You have to cite those sources. And this is going to be helpful so that I can try to determine what your knowledge is and what just someone else's knowledge is, right? I need to ensure that these exams are testing your understanding. I'm going to give you a warning right now on all of these things. I'm not going to have a lot of leniency on this if it becomes an issue, right? If you don't cite your sources and it's apparent that you copied from some other online source, you'll get a 0 on that, right? On the whole exam. You need to cite your sources if you're going to have this privilege of having the open internet, right? You have to cite your sources. Additionally, this is only singular work. You cannot work on this with other people, right? This is the expectation is that I'm evaluating you and your understanding. That means you can't talk to other people about the questions on the exam. I need to know if you know what's going on, not if your buddy knows what's going on, right? So the way I'm going to warn you on this, and this isn't going to be something that, on the second exam, if it's an issue, I'm going to ignore it, right? No. This is your warning right now. If there's even a suspicion that you cooperated with someone else, it's very likely that both of you are going to get zeros on the exam. And if it's egregious enough, you'll get Fs in the class, right? And I know that sounds really harsh and draconian and like, Scott, how can you do this to us? Well, don't work on this with other people, right? It's supposed to be singular work. If you're going to work on this by yourself, you don't have any issue, right? It's going to be fine. And you might ask the question, well, if you ask questions on your exam and I just happen to answer it the same way as someone else, why I'm concerned about that. That's okay, right? That's not a thing that has happened in the past, and that's not a concern I have in terms of determining if you worked with someone else. If you have questions about either of these, please let me know. Again, I need you to treat this with the respect that I am expecting, and what I mean by that is I need you to show the stuff that you know. And the reason is because I will ultimately give you a grade that will then determine to both people in our institution and people outside our institution what your understanding is. And so I need to know what you know, right? That's what we're getting towards. All right, enough of that lecturing. If you got questions on that, please let me know. I don't mind walking through it with you. All right, so topics for the exam. This exam for this week is going to be anything from vectors up to recursion. I'm probably not going to spend that much time talking about vectors. Most of it's going to be lists and then getting into stacks, queues, and dequeues. There'll be a little bit of questions about recursion, right? But in general, these are the spaces in which I'm pulling from. And now the only review I'm going to give you right now is essentially going to be just our complexity review. So first thing, let's go through this. The complexity of a vector, pushing back and pushing front. The push back is going to be, hopefully you're saying this out loud before I say it, OC if you don't have to resize, but ON if you do have to resize. Pushing front is always going to be ON, and in fact the STL vector doesn't allow for you to push to the front. You can do that with your own algorithm, but the data structure itself does not work that way. And then a deep copy is going to take ON, right? It'll take N operations to copy every element from one vector to another vector. All right, so popping back, popping front, random access, and then inserting and remove. Popping back, OC, good. Popping front, always ON because you have to shuffle everything forward. Random access, OC, and then inserting and removing is going to be ON. Now, the reason I'm showing you guys this and kind of what I want you to take from it is an understanding of why these are all ON or OC, right? I'm looking for that why, not the what. Memorizing this page isn't going to help you. Understanding how I got to these things is what you need to know. So for a list, let's keep going. If we're pushing back and pushing to the front of a list, it's the same operation. We're just adding a node. So that's going to be OC. And a deep copy, you're going to find a pattern as we go through these, is always going to be ON. All right, so popping back and popping front, it's very similar to pushing back and pushing front. Those are going to be OC. And then our random access, this is where we take a big hit. This is going to be ON because we cannot just randomly jump into a place. We have to iterate through our list and step through every single node. Now, the nice thing is inserting and removing, once we know what we're looking at, we can do that in OC time, constant time, assuming though that we know where we are. If you combine both of those two things together, the random access and the inserting and removing, really you're at an ON operation as well, but for different reasons than the vector. All right, so for our DQ is going to be able to do things a little bit different. So pushing back and pushing front, this is very similar to both a vector and a list, but both of those are going to be OC, because if we push front, we can just make a new array. And then our deep copy is also going to be ON. Now, right, this is the pattern. Deep copy means that you have to copy every element, which by default means that it's ON. All right, for popping back and popping front, those are also going to be OC, good. Random access, we still get that nice OC that we get from a vector, And then our inserting and removing, depending on how the DQ is formed, is going to be ON. It's possible we can make an advanced DQ that will treat this as OC. That's unlikely, though. It's most likely ON. All right, cool. Again, the goal behind this is to understand the why, not the what. Right? Just memorizing all of these things isn't going to help you. Understanding why pushing to the front of a list is OC is going to be much more important than just understanding that it's OC. All right, that's where I'm going to stop the review in this lecture. If you have more questions about this exam, please bring them to the class section. There is no homework for today. Your homework is just to start working on that exam. All right, if you've got questions, either get me on Discord or send me an email or bring them to that class session. We can work through them. All right, cool. Well, good luck on the exam. We will talk about it more later. All right, bye.